That is why I come here. So first I need to thank Gediminas to give me this nice invitation to come here. And I have heard so many fascinating talks. And this is maybe my first time to present our work before CUDA Atom audience. So I'm going to talk about our observation of chiral edge currents in superradiance lattices in hot atoms. And in this morning, we have heard several talks on room temperature systems, but this is quantum simulation in a hot atom. And we know that quantum simulation, have been realized in many systems, and we have a lot of candidates. And in the previous talks, most people focus on the optical lattices, and we have just heard one wonderful talk on photonic lattices. And there are other candidates. For the cooled atoms, they are quantum system governed by Schrödinger equation by the working very cooled temperature. Photonic lattices can work in room temperature, but they make an analogy between Schrödinger equation and Maxwell equation. And our work actually is a combination of the two. So we study the optical signal in a system, but at the same time, we are studying the quantum system. So basically, that is a well-known quantum optical system. You can think that is a standing wave coupled EIT system that we call it superradiance lattice because it demonstrates some very interesting lattice structure based on which we can do a lot of fun things. I will introduce that basically they are composed by time decay state, superradiance state. And in the previous years, we have proposed that we can observe band collapsing, dynamic localization, and we propose a scheme to realize the hot dam model. And there are applications. We can use these kind of states to make a quantum metrology. And in the experiment, we also realized optical isolation based on effective electric field in the momentum space. Okay, so basically, I'm going to talk about a new kind of momentum space lattice. So in the previous, we have a speaker, Cooper here. He was one of the first to introduce this kind of momentum space lattices that each site is different from each other by their momentum rather than position. And they have introduced some flux in this lattice. And recently, we have seen experiments in this direction by using BEC. And in Schneider's talk, we have also seen this extension of this lattice into 4 dimension. And actually, a lot of speakers here contributed into this area pretty much, including the realization of flux lattice in optical lattices by catalyst group and the synthetic dimensions. We have all seen these talks. Okay, so basically, what we have done is very similar to a work 3 years ago. That is the realization of chiral edge currents in bosonic and fermionic systems. But the only difference is that now we can do that in hot atoms. So this is a sketch of what we have done. Basically, we work in cesium atoms, and we couple the system with 2 standing waves. And then we'll probe the system and measure the reflection in different directions. And what we have measured actually is the edge currents in the 2 edges. This is a zigzag lattice, which has recently been studied by Gediminas in a very nice way. And we just implemented this lattice in the superradiance lattice structure, and then we observed the edge currents. I will introduce in detail later, but basically the state that compose this lattice is the so-called time decay states. They are collective excitations of the atoms, and it's a momentum space lattice, but not characterized by the recoil momentum, but by the phase correlation of the atoms. And this is a superradiance lattice. You can give him other names, actually. If you want, you can call that a multi-wave coupled EIT, because we have a lot of coupling fields over here. And you can also call that on resonance degenerate multi-wave mixing. It's not a four-wave mixing, but many orders of wave mixing process. Okay, so basically, let me first introduce what is superradiance. So first, superradiance was proposed by Dickey in the 50s that he observed Well, the different superpositions of the atomic excitations have different radiation behavior. For example, if you have a symmetrical superposition of two atoms, you are going to observe enhanced spontaneous emission. Otherwise, if you change the phase over here, you are going to observe suppressed spontaneous emission, which is called subradiance. And this has been a hot area since its finding, and actually in the 70s, it was already a very hot area, and the people observed a lot of interesting phenomena in hot atoms. And in the 90s, people observed that they can have two trapped ions, and they observed those enhanced and suppressed radiation. And Catalyst group observed this superradiance in BEC with the Raman scattering. And recent years, there are also a lot of interesting work in this direction. But what I'm going to focus on is in another direction that the quantum optics people are more interested in. That is, how about we go to another limit that the atomic ensemble is much larger than the wavelength of the light. That is just to the opposite of the decades model. So if we have a bunch of atoms in a size that is much larger than the wavelength, and you send in a single photon, and the single photon gets absorbed by the atoms, but you don't know which atom absorbed this photon, and effectively you couple the system into a superposition. A quantum superposition, you can actually have different probability amplitude over here, but the key factor is that you have a phase correlation of the different excitations. So it's like a wave, it's like a spin wave. And people have found that this kind of state can have directional emission. This is very important in our research. Actually, we just use this property to detect the chiron edge currents. Okay, so the first thing that when I look at this state is that, well, maybe, this is a wave, so maybe we can manipulate this kind of quantum superposition to measure something. So we think about, well, this is the oscillation of the phase. How about if we can maybe, to make a very fast oscillation of this phase factor, but still the system still contains just one photon, one excitation. But can we have a way to manipulate that we have a very large phase factor? And in this way, you are going to have a very fast oscillation of the wave. And by preparing the system in a proper way, you can make a measurement, right? You can make a measurement. Another interesting thing is that if you can prepare this state in a very fast oscillation phase factor, phase correlated excited state, then this is a kind of a subradiant state. You will not have a directional emission, and the spontaneous emission is in the order of single atom decay rate. Okay, so it turns out to be very easy. We just need to introduce another atomic level. And let's see, we first prepare the system in this superposition state with the zero phase correlation. And then we send in a pulse that drives the atom from excited state to another metastable state. The atoms emit a photon in the pulse, so it loses momentum. But this momentum is not a recoil momentum. It's a phase correlation between the atomic excitations. And then we send in a pulse backward to drive the atom back. The atoms absorb a photon from this backward pulse, so it acquires another negative momentum. So by doing this, we can have a larger momentum over here. So you can see that we can actually modulate this phase. We can change it to another phase factor. And we can repeat many times this process, just forward, backward coupling pair pulses, and we can have a very large phase correlation over here. And we have proposed a way that we can measure this phase to measure some very small displacement of atoms. But that will not be the focus of my talk. What I'm going to talk about actually is how about if we keep the two pulses a continuous wave, but not these pair pulses, alternative pair pulses. Then the system actually become a well-known system. It's just a standing wave coupled EIT system because we originally prepared the atom in the ground state. Then we couple this transition with very strong fields. And then we know that the atoms at different positions, this standing wave, will feel different coupling strengths. So the EIT spectrum will be different. For example, here I have a very small phase strength, field strength, so I have very narrow splitting. But here I have wider splitting. And then I just plot, the absorption spectrum of the whole system. That is just the average of all the spectrum, all the absorption spectrum. It looks like this. Then this is just reminds us about a very similar system that, well, if you have a tight banding model, and you calculate the banding structure very easy, and then you see that the density states have these two peaks over here. So the reason behind this actually is that these two systems actually are equivalent to each other. So this standing wave coupled EIT system is just equivalent to a tight banding lattice with two sublattices. And on each of the lattice, so each of the state is a time decay state. The prop field prepare a time decay state. Then the coupling field, we have two coupling fields in different directions, couple the atom to different time decay states with different phase correlations. So this is a lattice with different momentum. So it's in a momentum space, but the momentum is characterized by the phase correlation. And we can see that these two spectrum, one is the density states of the tight banding lattice, the other is the EIT spectrum. They basically overlap with each other. And this has been recently realized in a Bose-Einstein condensate. We can see this feature of the two peaks over here, but I'm not going to go into details of this paper. What I want to emphasize actually is that we can have a lot of extensions of this work. We have heard different talks on the dimension of the lattices. Okay, so let's go back to the EIT. Well, EIT, you just have plane wave coupling field that is effectively just a couple two time decay states. So it's a spinner. You just have two states that is zero dimension superposition lattice actually. And now I have one dimension just by adding a coupling field. So I can, for each time decay states, I have different states to couple. So that extends this system to a one-dimensional lattice. And if I have three coupling fields, then for each time decay state, it has three neighbors. So this is going to become a graphene structure, just honeycomb structure. And actually, we can introduce next nearest neighbor coupling very easily and realize the Haldane model. But this is not yet experimentally realized. So for higher dimension, we have seen that, well, just by adding coupling fields, it seems like you can have a dimension extension. So I totally believe the talks that I gave yesterday, because we have observed a similar structure. If you have four mode, if you have four plane wave coupling the atoms, you are going to have a diamond structure. If you have five modes, then you have a four-dimensional crystal. If you plot the band structure in a two-dimensional plane, you will observe something very similar to the quasi-crystal. And we have heard many interesting talks over here. Now, let me introduce what we have realized experimentally. Okay, so we basically, so let's see this three-level system, and we have one-dimensional, okay, let me see this. Okay, so we have two standing waves couple this EIT system. So one is far-off resonance, and one is on resonance. And this on resonance standing wave actually couple the system zigzagly. So this zigzag coupling strength comes from this on resonance standing wave, which just formed the superposition lattice I have just introduced. But I still have this off resonance coupling field, which actually couple the next nearest neighbors with the phase factor over here. The phase factor is determined by the spatial phase difference between these two standing waves. So we see actually this phase factor, spatial phase factor, introduce effective gauge field, effective magnetic field in this triangular placket. Okay, so each of the state, of course, is a time decay state. And in this kind of structure, I just want to emphasize that it's a collective excitation momentum space lattice, but not recoil momentum. And we have spin orbital coupling, but it's not like the spin orbital coupling in the Raman configuration. That is, we involve with the excited state, which is the key factor over here, because we need to observe the radiation later. And this is resilient to atomic motions, by the way. And we can detect the chiral edge currents by observing the directional emission of the superposition lattice. Okay, so before I show the experimental result, I want to talk about the temperature. Actually, the temperature is not a problem. Oh, thanks. It's not a problem over here. We have seen publications in the 1970s that people have investigated standing wave couple EIT system, they have found that the absorption actually is not dependent on temperature. And also recently, maybe 10 years ago, 5 years ago, people have found, well, the reflection spectra actually does not depend on temperature neither. So what we have done in the experiment actually effectively is like this. Okay, we have atoms prepared in the ground state. And then we pump the atom to the lattice, to the superconducting lattice in that in the atomic system I have just introduced. Then the excitations will actually go cyclotron motions in the lattice, go in one way or the other. Okay, this is a simulation of the population distribution of the excitations in this lattice. We pump at this zeroth site, and we find that in the steady state, the excitation will be guided to one side rather than the other because of these chiral edge currents. So in the steady state, we observe that, well, if you pump the zero side, you have a very big bias over here if you, depending on the phase. If you don't have phase, actually they are equal. But if you have a pi over 2 phase, actually they are going to be very different. And in the experiment, this is the structure I have just introduced. And the pump actually is generated by this probe field. I will probe the system in 2 different directions. And I observe the reflection of this probe field in these 2 opposite directions. That is effectively actually measure these 2 probabilities. So R plus, I probe the system in the plus direction, then get a reflection that is this side. And the other is on the right side. Okay, so this is very similar to what Xunjin Liu has introduced in the dynamical classification of topological phases, actually. And this is the experimental result. And we see that this is done in cesium atom D1 transition. We see that depending on the phases, okay, I forgot to label the phase, but this is 0, pi over 2, this is pi, and this is 3 pi over 2. So we see that the reflection in the 2 directions, all the probability of the 2 sides are very different if the phase is like positive or negative. And so this is just an in situ observation. You do the experiment, you see the monitor. What you have seen is that you change the phase, you are going to have these 2 reflectivities that change alternatively with the phase. And we have a simulation that can match the experimental results very well. Okay, so let me give a summary. So we have introduced a lattice that we can do quantum simulation. At least right now we can do single particle quantum simulation. And it has been realized in BEC, and now we realize in hot atoms and observe the chiral edge currents. We can use this to measure actually that phase, the phase difference between the 2 standing waves. And it has been realized in, to get a new kind of optical diode. And actually we can extend this to higher dimensions if there's interest in physics over there. And we can also introduce interactions between atoms or the collective excitations by readable states. So we have seen that from Paval's talk. And there's some other extensions or applications like we can do even high order wave mixing to synthesize different structures of the lattice, similar to what people have introduced in this conference. At the end, I need to thank my collaborators, Xiao Zhu, Jinxiang Zhang, and from my university, and Jing Zhang from Shanxi University. The theoretical work and the simulation were done by my postdoc, Han Cai, and the experimental work was done by Jinhong Liu, and assisted by the other 2 students. Thank you very much.